Hello, this is Dr. Gardner. In Chapter 8, we will be looking at how to predict Lewis electron dot structures and how to describe ionic bonding, covalent bonding, molecular geometry, and we'll be using concepts such as electronegativity and polarity of molecules, which will lead us into being able to predict the properties of molecules with respect to physical characteristics. So, to first develop these types of skills, we need to have already learned how to write electron configurations, orbital diagrams, and be able to determine the number of valence electrons you have in an atom. So if you have not learned yet how to predict numbers of valence electrons, you'll want to practice that before you work on drawing some of the Lewis electron dot structures, because you need to know the number of valence electrons in order to do this. So first of all, if we start talking about Lewis dot structures or Lewis dot symbols, once you determine the number of valence electrons you have, you're going to use dots to determine in the symbol the number of valence electrons involved in bonding. So first of all, when you count the number of valence electrons, recall that you're looking at the outer shell electrons of an atom, and this will exclude your d and f orbitals. Now, we did have some exceptions. If we had a transition metal where we had ended in the middle of the transition metal series, well, then we did treat the d electrons as valence electrons. But if we're in the s or p block on the periodic table, on the right hand or the left hand side of the transition metals, then we will assume that the number of valence electrons we have is equivalent to the number of electrons in the outer s and p orbitals. Now, these electrons are very important because on the outside of the atoms, those outer valence electrons will be involved in participating in chemical bonding. And as we start to look at predictions of chemical bonding, we're going to go ahead and use a very simple structure called a Lewis dot symbol, where we will use one dot for each valence electron in the atom of the element. Now, for example, if I consider carbon on the periodic table, if you look at the periodic table, carbon has 4 valence electrons. There's 2 2s electrons, and there's 2 2p electrons in the outer p subshell. And so if I count those 4 valence electrons, I'm going to use 4 dots around the symbol, and I tend to put 1 dot on each side of the symbol to indicate one of each of those 4 electrons. Now, we're ignoring all the d and f electrons, but those are going to be my core electrons in this case, and will not be involved in my general predictions in chemical bonding right now. So remember, each side of the element symbol that we draw is going to approximate for the concept of predicting Lewis electron dot structures one orbital in chemical bonding. So we're going to have our s orbitals and our p orbitals, and they're going to go through some processes that we call hybridization, where their character might mix. But right now, we're going to focus on the number of electrons and how they might be either transferred to form ionic compounds in some cases, or where they might be shared to form covalent bonds. Now, if I look at the S block, and by the S block I'm talking about where my principal quantum number n and my S subshells are filling up here in the S block. So I have my 1s, 2s, 3s, 4s, and so on. Or if I'm looking at my P block, and for principal quantum number for the row I'm looking at, and the P subshells filling up, so my 2p, 3p, 4p, 5p, and so on. In those cases, my valence electrons are being shown in this simple reference periodic table as the number of dots around the element symbol. So we had 1 valence electron for hydrogen, 2 for helium, filling up the 1s subshell. Then we had the lithium with 1 valence electron, beryllium with 2, where the 2s subshell was full. Then we have boron, where we have the 2s subshell full, and we start to fill the p subshell, the 2p, and then carbon has 4. Nitrogen has 5, oxygen has 6, fluorine has 7, and neon has 8. Now I want you to notice that when we fill up hydrogen and helium, it takes 2 electrons to fill the outer valence shell with those outer valence electrons. So we, in a sense, follows a duet rule. However, when I hit the second, third, and fourth period and below, we notice as we fill the valence shell of the S and the P subshells, we have 8 electrons filling up. So we're following the octet rule from here below. Now, once we get 8 electrons around my main block elements, we end up having electron configuration like the nearest noble gas, like neon or argon or krypton or xenon or radon, and they tend to be very stable like those noble gases. They tend to, once we get that number of electrons, gain stability from any chemical bonding that may allow them to gain that number of electrons, either by transferring electrons or sharing them, and at that point we predict quite a bit of stability. Now we will learn that as we start to involve d subshell orbitals, you can sometimes have what we call an expanded octet and break the octet rule, but for right now we're going to focus on situations where the octet rule is followed. Okay, if we consider what ionic bonding is, with ionic bonding what we have basically is electrostatic attractions holding opposite charged ions together and minimizing repulsions between the same charged ions as they stack together in an ionic lattice. Now, if we consider some common types of ionic compounds, let's go ahead and look at, let's say, sodium. Now, sodium's Lewis electron dot structure has a single electron in it. The reason for that is because there's just one electron in the 3s subshell. The rest are core electrons. So I've used an electron configuration here to indicate that. Now, if I draw chlorine, chlorine has a Lewis electron dot structure with 7 valence electrons. Now, I know actually chlorine exists in the gas state as diatomic molecules with 2 of these, but right now, as sodium and chlorine reacts, I'm just going to focus on one atom of each as I predict the chemical bonding. Now, the chlorine has those 7 valence electrons, and we can see that if we draw its electron configuration, we had 2 of those valence electrons representing 2 of the dots in the structure from the 3s subshell, and the other 5 of the 7 come from the 3p subshell. So it was very important that you practice drawing these electron configurations. Okay, so what happens when we have a metal like sodium reacting with a non-metal like chlorine is we can expect they have a very large difference in their attraction to electrons, which we will talk about later as electronegativity. But the sodium, the metal, tends to give up 1 electron in this case, since it only has 1 valence electron. The chlorine is deficient of 1 electron to have a complete octet, to be just like the noble gas argon after it. So it needs 1 more valence electron. So what happens is sodium will transfer its valence electron to chlorine, and as we do this we end up without any dots in the Lewis electron dot structure on sodium, but I have to indicate the charge as a positive 1 charged cation. So I just have its core electrons, the same core electrons that neon would have, which is a stable noble gas, so we expect the sodium cation to be quite stable with just 1 electron having been lost. And then my chlorine forms chloride by gaining that extra valence electron shown here color-coded in blue that it gained from sodium, and now it has the same number of electrons as argon, the noble gas that was after the electron configuration we had been looking at. It follows the octet rule and it forms the negatively charged anion. Now I want to point out, it's very important that you recognize here that you need to show the charges to indicate these are ions, and that when we form the sodium cation there are no dots in the Lewis electron dot structure, has lost all of its valence electrons. So this is showing you here that we now have an ionic compound. When we draw Lewis electron dot structures for ionic compounds, we never show lines between the ions, because lines would indicate a covalent bond where electrons were shared. In this case, we completely transferred electrons, so I do not want to show a line in my structure. Okay, since we start looking at this situation, we can realize that we have a completely empty 3p and 3s subset of subshells in sodium, and then we ended up having just that stable noble gas configuration. So please realize ionic bonding involves electron being transferred. Don't draw any lines between the ions. Okay, so if we consider what's going on with the energy in ionic bonding, well, you should realize there's going to be a net decrease in energy as we reach a more stable situation, because the bonded state is going to be more stable and at lower energy, which promotes the transfer of those electrons in the ionization process as we form ionic compounds. We can also realize we have a simultaneous transfer of electrons and formation of an ionic bond. So as we start to lose electrons from my cations, gain the electrons with the anions, we start to form an electrostatic attraction where the positively charged cation is being attracted to the negatively charged anion. Okay, so there's really 2 steps you can consider in ionic bond formation. First of all, an electron is transferred between 2 separate atoms to give ions, and then we have those ions starting to attract one another due to their opposite charges. That electrostatic attraction from Coulomb's law is starting to form an ionic bond where we have those attractions. Now, in the solid state, what we're going to have basically is an ionic lattice. This is due to electrostatic attraction between all of the dissimilar charged ions, between all the cations and the anions. The ionic lattice, where all these cations and anions are stacked together, will try to minimize repulsions between like charges. So the cations will tend to be placed further from other cations and closer to anions, and vice versa there. And the stacking of these ions in the ionic lattice will depend on the size of the cations and the size of the anions. And in more advanced courses, we learn to name the types of stacking we're going on. Sometimes we have simple cubic stacking. Sometimes we have more complex types of stacking that you'd learn if you continue on taking more advanced chemistry classes. Now let's predict some simple Lewis structures for the following atoms or ions. So if I have the lithium atom, it's neutral. It has not formed an ion yet. In this case, the lithium, if we look at the periodic table, has just one valence electron. So to help me predict the Lewis electron dot structure, it might be useful to draw a very quick electron configuration. I'm going to go ahead and use my noble gas cores to abbreviate these. So I have a helium core, and you might want to have your periodic table out here to make predictions. I have a helium core, and then I have a 2s1 electron configuration. Now my lithium then would have one valence electron, so I'm going to show one dot in its Lewis electron dot structure. So I have lithium and just one dot shown in its Lewis electron dot structure. Now if I form the lithium cation, what happens is we're losing this valence electron. So I ended up with just a helium core at this point for its electron configuration. So it just has its 1s2 electrons, just like helium. And we end up, when I form that lithium cation, I no longer have any valence electrons, so I just show the symbol for lithium with a positive charge and no dots around it for the Lewis structure. Now fluorine, if we have the neutral fluorine atom, if we consider its Lewis electron dot structure and its electron configuration first, well, its electron configuration still has a helium core, as we're looking at that second period on the periodic table. And we end up having, if we draw its electron configuration, first of all, we have the 2s2 valence electrons, and we have the 2p. In this case, we have 5 valence electrons in the 2p subshell, so we have 5, 6, 7 valence electrons. So when I draw the Lewis electron dot structure, I need to use 7 dots. I like to place one dot per side of the structure, first of all, before I double them up. So there's my first 4 of the 7 valence electrons. And I have 5, 6, 7. So I have one orbital that's half filled that could gain potentially one more electron to form an anion. So when I form the fluoride electron configuration, I gain one more valence electron to form a 2p6 electron configuration, which then gives me an electron configuration that's identical to neon at that point. And once I have that neon electron configuration, then I can draw the fluoride anion Lewis electron dot structure, and I have 1, 2, 3, 4, 5, 6, 7, 8 Lewis electron dots in my structure, and then I have to show the charge, so my charge is going to be a negative charge. Now you also see on some anions, it's often a good idea to put brackets around the anion to indicate all of these dots in my Lewis electron dot structure belong to the fluoride ion. They do not belong to any nearby cations. They have been completely transferred. So you often see those brackets. It's especially true if we have a polyatomic ion where we have multiple atoms involved in a polyatomic ion. You want to show those brackets to indicate the charge is basically associated with the entire polyatomic ion species, not just a single atom. Now let's consider a few other atoms that we can draw Lewis electron dot structures for. If we consider sulfur, well, the electron configuration will help me predict, or I can use the periodic table to help me predict the number of valence electrons. So first of all, since I only want to worry about valence electrons, I'm going to go ahead and just use noble gas cores. So for sulfur, we have a neon noble gas core. And we can see we're in the third period, so we start to fill in the 3s subshell, which will have 2 electrons. And then we have the 3p subshell. And the 3p subshell, if we look at that, we have 1, 2, 3, 4 valence electrons. So we have a total of 6 valence electrons in that outer set of subshells for the 3s and the 3p. So when I draw the sulfur's electron dot structure, I'm going to want to go ahead and show 6 electrons in the structure. So I show 1, 2, 3, 4, 5, 6. So we can see that there's 2 half-filled orbitals for sulfur that could be involved in bonding processes. Now when I form the sulfide anion, I can predict that the sulfide anion will form as I gain 2 more electrons, because there's 2 valence orbitals that are half-filled that we could gain 2 electrons in from cations present, and so we can go ahead and form the sulfide anion. As the sulfide anion forms, what's happening is we end up putting 2 more electrons into the 3p subshell, and so if I'm looking at the electron configuration for sulfide, we end up with having a 3p6 in that case. So we have a 6 there. And so I end up having 6, 7, 8 valence electrons. So I can go ahead and put my valence electrons in. 1, 2, 3, 4. I like to put 1 per side before I double them up. 5, 6, 7, 8. Okay, and then I will put a square bracket around it, indicate it that we have a total of 8 valence electrons that are in a sense owned by the sulfide anion, and we show the charge outside the square bracket, so we have the sulfide anion there. So that indicates that it had gained 2 electrons. It filled its valence shell, and we're following the octet rule. Notice that for the sulfide and the fluoride and the sulfide, we end up following the octet rule as they formed ionic compounds. They have a full set of 8 electrons around them, and that indicates that they have stability like the nearest noble gas. For example, the sulfide now has the same electron configuration as argon. So we have an argon electron configuration here that we could talk about for stability. Now let's consider the metal indium. So if you look on the periodic table, below aluminum there's gallium, and below gallium there's indium. If we look at indium, we can go ahead and look at its electron configuration. Its electron configuration is going to have a krypton core. So we have a krypton core here. And that krypton core, then we have, after krypton, for the indium configuration, we have our 5s. So we have a 5s2. We look at our periodic table there. And then after the 5s2, we have a 4d. So we're filling in our d orbitals there for indium. And so that 4d is completely filled, so a 4d10. And then after the 4d10, we have, in this case, my 5p. And for indium, we just have 1 electron in the 5p subshell, since it's the first element in that subshell in the 5th row of the periodic table. So we have a total of 3 valence electrons, because remember, a filled d subshell is stable, and we do not predict that it's going to form ionic bonding or covalent bonding by sharing or transferring those electrons. So my valence electrons are just the 5s2 and the 5p1, so I have 3 valence electrons. So if I draw the Lewis electron dot structure for indium, we're going to go ahead and just put 3 dots around it to indicate those 3 valence electrons that are available to potentially form bonding. And if I formed the indium cation, well, I had 3 dots in the Lewis dot structure. I had 3 valence electrons. Also in the electron configuration, I can see that. And so the indium cation has lost all 3 valence electrons, and we end up with having a 3+ charge on indium. Okay, so this is the basic way I will draw Lewis electron dot structures for individual atoms or for ions they might form. The next thing we want to practice is drawing Lewis electron dot structures for basically ionic compounds when I have both the cations and the anions present. So let's go ahead and take a look at that. Now I want to stress here that when I'm looking at ionic compounds and I draw their Lewis electron dot structures, I should not, this is very important, I should not draw lines between the ions, because lines would indicate shared electrons that tend to occur in covalent bonding, where we usually have covalent bonding between just nonmetals, where we haven't completely transferred electrons. With ionic compounds, we're completely transferring electrons, and so I shouldn't show a line. Their electrons are not shared, so I just show the dots for those valence electrons on the atoms they're located on and the ions themselves. So be very careful. No lines for ionic compounds. The reason I'm stressing this is I often see students forget this, because after we practice drawing ionic compounds, we'll have many students start to look at Lewis electron dot structures for molecules, where we start drawing lines to indicate covalent bonds, and we do quite a few of those in the course. And then students forget with ionic compounds not to draw the lines. They start to try to draw them like a molecule, and they're not molecules. They're formula units indicating the ionic lattices where the charged ions are stacked together. So please, no lines for ionic compounds. Remember that, because you're going to have to draw some of these on the test, and if you draw those lines, that you will have an incorrect structure. So first of all, let's consider what's going on when we have lithium reacting with fluorine. So if I have lithium reacting with fluorine, well, the lithium neutral atom has one valence electron. If we consider fluorine's Lewis electron dot structure, it had the 7 valence electrons. So you put 7 dots around it. And so what happens is, as we form a compound, the lithium's valence electron is transferred, and we're going to form a cation from the lithium and an anion from the fluorine. So we form the lithium cation. The lithium cation is going to have a positive charge with no valence electrons, so there's no dots around it, and there's no lines drawn to the lithium cation. So just remember, don't draw lines to your cations in this case. And then when I form the fluoride anion by gaining an electron on fluorine, we end up having a complete valence shell. So we're following the octet rule. Fluorine now has an electron configuration like neon, and so it has all 8 of the electrons. We completely transferred that lithium's valence electron, so now fluoride that is formed will go ahead and own 8 valence electrons to follow that octet rule. And you go ahead and practice drawing these as well as we're going through these. I'm going to show square brackets around the fluoride to indicate all of those valence electrons belong to the fluoride. They no longer belong to the lithium. And we show the negative charge of the anion that's formed in the upper right hand corner. So we're predicting the most stable types of ions that can form, but we're also seeing how that relates to the valence electrons that we have looked at before in the electron configurations as we form these cations and anions. Now let's consider potassium and oxygen. If we have the potassium elemental atom, it has 1 valence electron. If we have oxygen, well, if we look at oxygen, there's 6 valence electrons in its electron configuration. If you need help with that, go ahead and pause the video, draw the electron configurations out first of all to see the valence electrons. And so we're going to have a total here of 6. And we can see then that we have a half-filled orbital, and then we have another half-filled orbital. So we have 2 half-filled orbitals that are available for bonding. In this case, we can start to have electrons transferred. Now, if I transfer an electron from a potassium atom, that will give oxygen a -1 charge, and it will have 7 valence electrons. Now, we learned early on to predict that as we formed ions from oxygen, we tend to form the oxide anion, which has a 2- charge. And so it would have to gain 2 electrons. So where would that second electron come from? Well, if we can, in this situation when we're predicting ionic bonding, we could have another metal cation. We can go ahead and make that type of prediction. If we have another metal cation, we have another valence electron, and that valence electron could be transferred to form another cation. And we can end up with 2 electrons transferred to fill the octet around oxygen to give it all 8 electrons it needs by filling both of the half-filled orbitals. And now we can end up having a potassium cation in the ionic compound. We have oxygen with all 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. And then we show square brackets around the outside that is formed and the charge on the outside. Now I'm showing the square brackets to indicate all of those Lewis electron dots belong just to the oxygen because it has formed the anion. And then I have a second potassium cation that has formed. Okay, now if you add up all the charges here, we see we're charge balanced. We have the 2 minus, we have 2 plus 1s. In fact, when you in the past have drawn the when you have written the ionic compound formula here, you would have written K2O for potassium oxide. We can see that makes sense with respect to predicting what's going on with electrons, with those valence electrons, and my Lewis electron dot structures. Notice I have not drawn any lines between the ions and the Lewis electron dot structure because there are no shared electrons. There are no covalent bonds such as we see in molecules. Now let's go ahead and practice just one more of these today. If we go ahead and look at the aluminum element, aluminum has 3 valence electrons. If you look at the periodic table, it has a 3s2 and 3p1 electron configuration right after neon's core, and so we have 3 valence electrons. And then if we consider bromine, well, bromine has 7 valence electrons, right? Bromine is going to be right after argon. We have a 4s2, 4p5 electron configuration, so we have a total of 7 valence electrons. So we have 1, 2, 3, 4, 5, 6, 7 valence electrons. Now what can happen is aluminum can lose one of its valence electrons to fill the octet on bromine. This would form bromide, right? We'd have a total of 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. We show brackets around that. That's the bromide ion. But at that point, if that's occurred, I have aluminum with only a +1 charge. And we learned that aluminum should have a +3 charge because it's going to lose all 3 of its valence electrons. And so we need to have 2 more bromines. So I'm going to go ahead and have my next electron lost to a second bromine to form bromide, and so we're going to go ahead and have 1, 2, 3, 4, 5, 6, 7, 8, a full octet. It has the same electron configuration for bromide as krypton after the element, and I put square brackets and a negative charge. Okay, and so this bromine is no longer present. I have that bromide, and then I'd have to have a third bromine present that now has gained this last valence electron, and so I will go ahead and have 8, whoops, sorry, that should be a dot, 1, 2, 3, 4, 5, 6, 7, 8 valence electrons with a negative charge. So I have 3 bromides, and now the aluminum, since it has lost these valence electrons, has a +3 charge. So I need to show 3 bromides and 1 aluminum cation. And you could draw this a little neater on your paper, but that's basically what you have here. So you had to indicate charge balancing. So if I had ever drawn out the formula for this compound, if I'd written the formula, I'd have aluminum bromide with 3 bromides in the structure, so we can see that it was charge balanced. Now we're just indicating what's happening with the valence electrons when we show the electron Lewis dot structures. Okay. Now realize we don't actually just have a 2-to-1 type of molecule. We have no molecules at all here. We actually have an ionic lattice, so we have a bunch of ions that are stacked together in these cases, and we're maximizing attraction, Coulombic attractions due to charge, opposite charges between the cations and the anions, minimizing repulsions between the like charged species, and so that's really what we have here. So our next tutorial video will be looking at covalent bonding, where we start to share electrons and draw Lewis electron dot structures. Now if you have extra time today, please practice drawing a few more Lewis electron dot structures with your local instructor. Make sure you can draw them for sodium chloride, that you could draw it for a few species with +1 or -1, +2 or +-2 charges. Make sure you have polyvalent ions. So if we have +2 or -2 or a +3 or -3 type charges. Make sure you can draw those. So practice a few more. Okay, have a great day, everybody.